let's go. Okay, let's continue our course. One more addition to the toolbox. This is called Hilbert transform. Okay, idea. Let's say I have a signal what can be presented as a Fourier row or in form of Fourier series. So it can be written as a sum of harmonics omega plus vk. Where I can write vk is a square root of ck squared plus sk squared. I want in inverse. In inverse, okay, k is ak cosine of phi k, and sinus is minus ak sine phi k. No, okay, I wrote it. It's easy. It's easy. But from this, I can take a look from, how to say, different angle. What angle? See, I have frequency. One of the frequencies, omega k. I can draw a system of coordinates. So, at any moment, I can say what I have a vector with magnitude ak and angle phi k. This projection, this ball projection, what's a magnitude of it? ak cosine of what? This vector rotates with the speed omega k. So here will be omega plus phi k. What it is? My signal. Blue line projection. I can assume that my signal is blue line. But it's not all. I can draw a red line. This will be sine projection. Precisely, it's an ak sine of omega plus phi k. Another projection of my signal. This is equal to ck sinus omega minus sk cosinus omega time. Now, what I see, all red lines, all these red objects, red projection, how to say brother of my signal. It's somewhere k starts from 0 to infinity of sine omega minus sk cosine omega. This is a conjugation of my signal. It's a conjugated signal to my original signal. Simone, I can do one trick. I can write that my signal is kind of cosine c from time. What I'm writing? Let's say this is my signal. I can draw a borderline connecting on maximus. Here is my time scale. White line is my signal. Red line is a borderline for my borderline what's enforced? It's a square root of my signal plus conjugated signal in square. Instant angle is arctangents I can assume what in my signal y borderline. I can assume that this line, red line, is product of some vector. There is a vector drawing this line. So any signal that can be represented as a Fourier series can be represented as a vector via introduction of this conjugated signal. Couple notes on borderline. When conjugated signal is 0, borderline equals to my signal, original. If we take a derivative, sorry. If we take derivative, we will see what my signal first derivative should be here, what should be added. At the moment, at this moment, at the moment when conjugated signal is 0, derivatives are equal. And one more note. Always greater or equal. The borderline never crosses with signal. Now, if we take a look on a signal with frequency range from omega min, omega max, in such way what omega max and omega min is much less than omega max plus omega min by half, meaning narrow band signal. We will see something looking like close to harmonic signal with slowly changing angle. If we write our full phase as a kind of omega it's an average. It is omega max omega a plus divided by half. So average central point of frequency plus kind phi 0. This phi 0 will be something will change slowly. It's because we have a narrow relatively narrow frequency range. Remember frequency modulation. We can do one thing. There is a theory behind, it's in depth of Fourier transfer theory saying what? This conjugate function can be found as a convolution here should be t minus tau. Signal itself can be calculated from, obtained from its conjugation. Here should be minus 1 divided by p, integrate the tau. Name for this is Hilbert's theorem or Hilbert transform. It is not possible to calculate Hilbert's integrals directly. So Hilbert's transform should be substituted infinity to infinity tau t minus tau. The tau should be calculated in an epsilon over 0 of minus infinity to tau minus epsilon n from tau t minus tau the tau plus in tau plus epsilon to infinity s from tau t minus tau t tau. Yeah. There is one thing. Sigma and S are forming quadrature. There is 90 degrees phase shift between them. P by half shift. Idea of this conjugated signal allows us to introduce vector representation for any signal that can be presented as a Fourier series. There is no necessity for it to be harmonic. Complex representation for any signal is signal itself plus its conjugate. This means absolute value is square s squared plus sigma squared from time equals to magnitude of borderline and argument of this compass equals to angle. Now question. What is Fourier Fourier representation of conjugated signal. What we will see in frequency space. Spectral function, we need to take Fourier transform. Follow. What we will get? One divided by p minus infinity to infinity. Here we can leave one a power omega time in minus infinity to infinity. Wait, this is not correct. One moment. Here I'm writing Hilbert theorem. Tau O. To integrate this, one of the way is to introduce V as a substitute variable as t minus tau. dv will be same as dt. Now we need to replace a power j omega v by the Euler's formula, and we will get our spectral function in the form s from tau a power minus omega tau. The tau multiplied by minus infinity to infinity cosine of d minus your sine omega v divided by dv dv. Internal, that's what I left on the first page, can be equal or square root of minus 1 j at negative frequency, or minus j in case of positive frequency. This one, yeah. On the other side, this one is plus minus j, and the previous one is a spectral function of my signal, but no, it's okay, it's a spectral function. This means what I can write following. Gs from omega when omega less than 0 and minus your gs from omega when omega is positive. Gs is a spectral function of my signal. Since Fourier transform is linear, Foxy spectral function will be omega plus dot sigma from omega. Or 1 second, I will write it. Full, sorry, this one from omega equals to 0, omega less than 0, and double when omega is positive. Inverse Fourier transform with such a result is known. It will be 1 divided by p integral from minus infinity to infinity e from omega a power of omega the omega. This will yield 1 divided by p integrated from 0 to infinity. My signal spectral function a power of omega times the omega. I can find complex signal directly through spectral function. Now, let's see something. Familiar. Harmonic signal. Simple case. I have a simple harmonic signal. O max cosine omega time plus phi 0. Can be rewritten as O max cosine phi cosine omega 0 minus sine phi 0 sine omega 0 time. Conjugated one, conjugated signal will be O max cosine phi 0 sine omega 0 time minus sine omega 0 time sine phi 0. Halt. Cosine, sine phi 0, mistake here, cosine. This equals to sine omega 0 time plus phi 0. Quadrature. They are shifted by 90 degrees. Complex representation or complex signal corresponding to this will be equals to max cosine omega 0 time plus phi 0 plus dot sine of omega 0 time plus phi 0. Can be written as a power dot omega 0 time plus phi 0. Here is complex representation of my harmonic signal. So familiar from electrotechnics theory. I can introduce complex magnitude as a power dot phi 0, and my complex will be complex magnitude a power dot omega 0 time rotation of complex plane. Here, Hilbert's theory gives a foundation for complex representation of AC currents and any thing what can be presented as Fourier series. You can have complex or phasor representation for anything what can be presented as a Fourier series. Yes.